Welcome to Lesson 6C, Evaporation Introduction. This is the first of a few modules that we'll have on evaporation. I want to talk first about evaporation of pure liquids. What we're going to do is consider some volatile liquid like a VOC, volatile organic compound, and we're going to consider a pure one. It's not mixed with water or anything else, so pure gasoline or pure benzene or something like that. And it has a liquid surface that's exposed to the air. So you're sitting in some kind of a container or in a puddle on the floor or something like that. We call this an interface, the surface exposed to the air. So the air will be an ideal gas mixture because you will have this liquid evaporating. Now we'll generally consider a steady state case. So this has been happening for a while, and this is the setup that you'll have then. This is the liquid, VOC. And this is the mole fraction Y. And I'm plotting two things. In red here is the species. So this is Yj as a function of elevation Z from the liquid surface. By the way, this triangle means a liquid surface exposed to the air. That's a universal symbol that I also use in my fluids book, so you've probably seen that before. We put in some plane P here. So what's happening is this liquid is constantly evaporating, and then those vapors are going out into the air. So we assume this is a very big room up here. First of all, let's define this Nj. It's called the molar flux, the number of moles of species J crossing a fixed plane P, and it's per unit area per unit time. Dimensions of Nj are N, number of moles, which is one of our primary dimensions, over L squared T, area and time. And the units are typically moles or kilomoles, generally kilomoles per meter squared per second. You can also define an Na, which would be the same thing except for air. In this case, we're talking about only air plus the species, the VOCJ. This is the molar flux of liquid that is evaporating, so it's now vapors that are crossing this plane. I also plot Ya of Z, so this is the mole fraction of the air. And of course, there's another important equation that we learned way back in the first week, and that's sigma Yj is equal to 1 for any mixture of ideal gases. And here there's only two species, so we know therefore that Yj plus Ya equal 1 everywhere. And you can see that I plotted it that way when we have this value of Yj, Yji, so that's the value at the interface. This would be Yai, the mole fraction of air at the interface. And these go from 0 to 1, of course, mole fractions. So you can see I sketched it so that Y of the air plus Y of the species would give you 1 when you add those two up. That's true for any Z location. When you get up near the top here, at this location, you have approximately pure air. Therefore, Ya is approximately 1 and Yj is approximately 0. You can see this going to 0 and this going to 1. The other thing I wanted to point out, you may recall from early on in the course, we defined Xj as the mole fraction of J in a liquid, just like Yj is the mole fraction of J in a gas. So here, Xj would have to be 1 since it's a pure liquid. Later on, we're going to modify this and look at some combination of water and some chemical. Notice that since Yj plus Ya equal 1 everywhere, then as Yj goes down, Ya goes up and vice versa. Now we're going to consider the interface, the surface of the water. At the interface, here's my liquid that's evaporating. What I want to talk about is this value, Yji, and this value, Yai, for the air and the species J. It turns out that for a pure liquid, Pj, the partial pressure, equal Pvj, the vapor pressure or the saturation pressure at the surface or the interface. So Pji is equal to Pvj. And that is a very important piece of knowledge because we'll be able to figure out how fast this evaporates based on that value of vapor pressure. So in other words, at the surface, the air is saturated with vapors of the VOC. if you have a glass of water and you would put a probe that measures relative humidity and get it just above the surface. So we're talking about right here, just above the surface of the liquid. The partial pressure would be the saturation pressure of water at whatever temperature that is. Same is true with this VOC. And we recall Yj is Pj over P, and here P is just the atmospheric pressure. We can combine these two and get Yji equal PVJ over P, or P atmosphere, and then Yai equal 1 minus Yji equal 1 minus PVJ over P atmosphere. So now we know the mole fractions Yai and Yji just by knowing the vapor pressure of the liquid, since it's a pure liquid. Now Nj, this molar flux, that's a measure of how fast this is evaporating. So just qualitatively here, it goes up as PVJ goes up. In other words, you have faster evaporation when you have a bigger PVJ. So something that's very volatile, like gasoline, you can smell it real quickly and it has a very high vapor pressure, so it evaporates quite quickly. And there are other substances that would have a low PVJ and then they would evaporate more slowly. What I wanted to do now is give you some physical explanations of what's going on. I'm going to give you 3 different physical explanations. The first one I'm going to call loss of liquid. Let's consider a container that has some VOC that's evaporating. So this is at some time t and some time t plus delta t. We have this partially filled with the liquid VOC, and this is just air above it. What happens? Well, it's evaporating. The equations we give will be steady, but we call it quasi-steady because this is happening very slowly. So at any given time, we can use our equations. But if you wait a long time, you actually lose that liquid. Take a cup of water and stick it on a shelf and come back a week later, and it'll be a lot lower in level than it was because a lot of it evaporated. Let's consider our plane P here, and we're saying that there's some Nj coming across that plane P due to this evaporation. By the way, this is the Z direction going up. We have Z defined from the liquid surface locally, wherever that liquid surface is. Think of it in terms of loss of liquid. So if I look across here at these 2 different times, this entire chunk of liquid at T is no longer there at T plus delta T. This liquid has evaporated in the time period delta T. It's gone. It's no longer here. So what happened to it? Well, that's why we have a molar flux. We have moles of the VOC coming across this plane and going into the room. And that's because we've lost liquid. It had to go somewhere, and that liquid turns into vapor, which is a lot less dense, and it just goes out into the air. The opposite thing for the air, if you think about time t, we had all this liquid, and now we have this whole chunk of air. So air has displaced the liquid, which has evaporated. So where did that air come from? You have to have another N, and this is NA of the air coming down to fill in that gap. This is a diffusion process. The air is moving from big to small z. Species is moving from small to big Z. So the bottom line is NJ is positive in the Z direction and NA is negative in the Z direction. And this is both across P, and that's happening through the whole time. So that's one way to understand this. The second way is from what I introduced last time, the gradient diffusion analysis. Recall, one of the main takeaways from that lecture was a species diffuses from a high concentration region to a low concentration region. Again, if I draw surface, and here's my Yj as a function of Z, this is Yji at the interface. C concentration is proportional to mole fraction, so you can think of terms of ppm or mass concentration, whichever you want. But this is a high concentration and this is a low concentration. Therefore, as I kept sketching with gradient diffusion, we have a J here is Nj that's going up. Jj is relative to the moving vapors, whereas Nj is relative to some fixed plane. So we take this plane P here, and that's a fixed stationary plane. and we're just looking at the mass or the molar flux across that plane, whereas JA would be relative to the moving net motion of that vapor up, as I explained here, because of this displacement.
I like this second option the best. We know, Albert, but unfortunately,
we're going to dispense with the J for now and talk about NJ only. By the same token, if you plot the air concentration or mole fraction, we have the opposite because we have a high concentration at the top and a low concentration at the bottom. NA is negative, going in the negative Z direction. NJ is positive, going in the positive Z direction. And that agrees with loss of liquid physical explanation up here. So that's two different ways to think about it. There's a third way, and that's in terms of partial pressures. Now, again, from the first week of class, Yj is Pj over P, and this P is a constant. That's just atmospheric pressure. So we can plot Pj and Pa versus Z. Pj is directly proportional to Yj, so they'll have the same shape as Yj and Ya. So these sketches will look exactly the same, just have different units. If I plot Pj or Pa, and this is actually what we're going to use more than Y. We're going to use partial pressures because we can easily look up the vapor pressure of liquids, and then we'll use that as our analysis. Instead of 0 to 1, we have 0 to P, atmospheric pressure. That'll be the maximum. And our Pj will be somewhere lower than that. And so our Pj will look something like that. And this will be Pj at the interface. And then for the air, we'll go up like this. And eventually this goes towards P. This goes towards 0 when you're far enough above the interface. Again, there's an NJ in terms of partial pressure because partial pressure is also a form of a concentration since it's directly proportional to mole fraction. So we're going from a region of high concentration to low concentration. And then, of course, the air is opposite. So that's how you can think of these physically. And this is what we're going to be interested in because for a pure liquid, Pji must equal Pvj at the interface. The gas mixture just above this interface, Pj, if you'd measure it, it would be Pvj. We can look up Pvj in tables for given substances. I'll show you that in a second here. There's one other thing that's important, and that is that the molar flux, Nj, also depends on dAj. Remember, that's the binary diffusion coefficient, dAj, as any diffusion coefficient is length squared over time, and the units are in meters squared per second in SI units. And so let me just summarize here. The larger dAj is, the larger Nj is. In other words, there's more evaporation. And the larger Pvj is, the larger Nj is, more evaporation. I want to show you how to get Pj and dAj from tables. There's two tables in the appendix. I'll look at PV first. The vapor pressure, just a comment, the online pocket guide by NIOSH that we use all the time that has those MSDS or SDS sheets, these are at 20 degrees. So if I give you a problem that's at 20 degrees, you can just look it up on the online pocket guide. But at other temperatures, you have to use Appendix A8. This is a weird table because the values in the table here are actually temperatures. And then these are your vapor pressures in terms of millimeters of mercury. Same units that you find on the online NIOSH pocket guide, actually. Let's look at benzene, which is a common chemical, at 30 degrees C. Now, if you're lucky, 30 degrees C would be one of the temperatures along this benzene row. But you don't have 30 degrees, but 30 is in between these two. So you have to interpolate. We know our answer is going to be between 100 and 200 millimeters. If you're not familiar with interpolating or you forget how to do it, I'm going to point you to my YouTube channel. There's a video called appropriately linear interpolation. Go through that and get refreshed. Let's just write Pvj at 30 degrees C is equal to 100 plus 30 minus 26.1 over 42.2 minus 26.1 times 200 minus 100, and that's equal to 124.22 millimeters of mercury. If you want to convert to kPa, which is what we usually want to do, 101.325. kPa is 760 millimeters of mercury. So PVJ is 16.56 kPa. So you can see that benzene is a fairly volatile liquid because it's 16 kPa out of 101. So that's a pretty large percentage. I did a quick interpolation with these tables also for 20 degrees C. I get 77.2 millimeters of mercury, and the NIOSH pocket guide gives 75. They're pretty close. I'm not sure why they're different other than we're interpolating, and this is not a very fine interpolation, so the 75 is probably more accurate. We're good to about 2 digits for these kind of things, not much more than that. And then finally DAJ, this is Appendix A9. The column that we're interested in is here. There's also water diffusion coefficients and Henry's law constant, which we'll talk about later. But for now, let's look at this, and we're talking about benzene. It's the 0.77. Assume that DAJ is approximately constant. It's independent of temperature, so you don't have to do any kind of interpolation. You just get this constant. These are independent of temperature for a certain temperature range, but we're just going to take that for any temperature. In the table, in the book, we call it DJ air. I'm just calling it DAJ equal DJ air. And the other thing is this factor of 10 to the minus 5. Here, DAJ for benzene is equal to 0.77, and you multiply by 10 to the minus 5 meters squared per second. And if you forget whether you're supposed to multiply or divide, think about kinematic viscosity for air is right around that same number, 1.5 times 10 to the minus 5 meters squared per second. These diffusion coefficients are all very close to each other. You can see these are all around 1 or 2 times 10 to the minus 5 for all these chemicals.
I like this second option the best. Thank you for watching this video. Please subscribe to my YouTube channel for more videos. 1, 2, 3. That's all there is to it.